Hello and welcome back to Hilbert Spaces, the video series where we talk about linear operators on inner product spaces, their adjoints and related stuff. And indeed, in today's part 19, we continue talking about the properties such adjoints have. These properties are really important because later in the series we will prove some important theorems for so-called self-adjoint operators. And as always, here at the beginning, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. If you want to become a member on Steady, please check out the link in the description. And then without further ado, let's start and let's consider two Hilbert spaces X and Y. And this means that in general, we also have two inner products, one in X and one in Y. And now, as we have already discussed, for every bounded linear operator T between X and Y, there is a unique adjoint. This adjoint is an operator from Y to X and usually denoted by T star. And as we have discussed in the last video, this T star is uniquely determined by an equation with the two inner products. Namely, we have the inner product in Y with T on the left hand side and in X on the right hand side considering T star. More precisely, we have ytx here and t star yx there. And we want to have this identity for all x in x and y in y, and then we know that t star exists and is uniquely determined. So this is something you should remember. This adjoint operator always makes sense for a bounded linear operator between two Hilbert spaces. And now, as promised, let's prove some important properties of this adjoint operation. And now the first thing I want to discuss for our bounded operator T is the double adjoint. Obviously, the adjoint of T star will be an operator from X to Y again. In other words, what we do here is to apply the star operation again. And obviously, usually we will omit parentheses and just write T double star. This is a really nice notation, but now the claim is that we actually don't need it, because the result is the operator T again. So applying the adjoint operation 2 times does not change anything. Okay, and then the second property is about the operator norm of T star. And indeed, it does not change, it's the same as the operator norm of T. This is quite nice and it might not surprise us, because T and T star act in a similar way, because they just change positions in the inner product. And in fact, this also implies a relation between the kernel of T star and the range of T. Namely, if you take the orthogonal complement of the range of T, you get the kernel of T star. And please note, this also implies that you can take the orthogonal complement on both sides. And this means that the orthogonal complement of the kernel of T star is the closure of the range of T. So there are two things that are really important to remember. First, a kernel is always a closed set, but a range is not always a closed set. Indeed, in linear algebra, when we only have finite dimensional vector spaces, we don't need this closure here, but in the general infinite dimensional case, we need it. So please don't forget that, in general, the range of an operator is not closed. Very well, and then I would say we are ready to prove this nice 3 properties. And for the first one, we can just use that the adjoint of any operator is uniquely determined by this formula. So more precisely, now instead of T, we would consider T star. This means the left hand side looks like X T star Y in the inner product of X. And then on the right hand side, we just have the adjoint of T star. This means we have T star star applied to X with Y in the inner product of Y. And as always, this identity holds no matter which vectors from the two Hilbert spaces we choose. And at this point we can just use that the inner product is conjugate symmetric, which means we can exchange the order in it. The only thing that changes then in the complex case is that we have a complex conjugation on it. But ignoring that, we see that inside here we can use our defining property for the adjoint of T. This means now we have T on the right hand side and the inner product in Y. Also this one we know holds for every vector X and Y. And now we can just exchange the two entries again to get rid of the complex conjugation. And this is already our result, because here on the right hand side you see that t star star should be equal to t. And indeed, to make this clear cut, we can just bring the one side to the other one by subtraction. And then on the left hand side, inside the inner product, we just get t star star minus t applied to x. And moreover, we have y on the right hand side, and the inner product is equal to 0. And now the first crucial part here is that this holds for all y in y, which means the only possibility is that this vector on the left hand side is the 0 vector. And moreover, it's the 0 vector no matter what x is, so t star star has to be equal to t. So this is the whole proof for part 1, and now we can use it to also prove 2. In fact, there we already know from the last video that the operator norm of t star is bounded by the operator norm of t. In other words, at this point we only have an inequality, but we want to extend it to have the full identity. And in fact, this is quite simple, because we can just use the property from the first part. Namely, on the right hand side here, we can just substitute t with t star star. And now obviously, the inequality also holds for this adjoint. So more concretely, instead of t, we would write t star in our first inequality here. Hence, what we get here on the right hand side is the operator norm of t star again. And now, since the left hand side is equal to the right hand side, we know that all the inequalities in the middle are actually equalities. And there we have it, the operator norm does not change if we go to the adjoint. And now finally, in the third property, we talk about the kernel and the range. And in order to show the equality, let's go to the elements. So let's take a y from the kernel of t star. So by definition, this means that t star sends y to the 0 vector. And obviously this is also correct if we put this 0 vector into the inner product. So what I mean is that t star y together with any x in the inner product is still equal to 0. In fact, in this case, it does not matter at all which vector x from the Hilbert space x we choose. However, if we know that for all x in x, we know that this vector lies in the orthogonal complement of x, which is just the 0 vector. In other words, we also have the other implication here, so we also have an equivalence. In addition, in this inner product here, we can also use the definition of the adjoint, which always means that we can just shift t to the right hand side. And now this is equal to 0, and it holds for all x in x. Therefore, what we actually do here is that we go through the whole range of t. And the name for the vector could be y tilde, so y tilde goes through the whole range of t. So what we get is that this inner product vanishes for all points in the subspace, so y lies in the orthogonal complement. And most importantly, this is also an equivalence, so we have equivalences through the whole proof. And this simply shows us that these two sets here are equal. And with that we are finished, the proposition is shown. And this last property is really important, and you definitely should remember that, because it means we have a decomposition of our Hilbert space Y. More precisely, what we have here is an orthogonal sum. So if this one is the kernel of t star, then orthogonal to that we find the range of t. And again, since the range is in general not closed, you should close it and remember the decomposition in this way. So the result here is that every vector in Y can be written in a unique way as a sum of two vectors from these two spaces. And not so surprising, we can use the adjoint of the adjoint to have the same picture in X on the left hand side. So for example, we could say that this is the kernel of T, which is the same as the kernel of T star star. And then orthogonal to that, we have the range of T star. And also here, please don't forget that we need the closure for the range to have a decomposition into closed subspaces. So there we have it. Hilbert spaces can be split into an orthogonal sum if we have a bounded linear operator T. And now for the end of this video, I want to show you some more properties for this nice adjoint operation. Indeed, these are really easy to prove just by writing down the definition of the star operation. So first, if you scale a vector and then you apply the adjoint, then you can also pull out the scalar. The only thing that happens, as you can see in the inner product, is that we get the complex conjugation of lambda. This is quite simple to show, so I just state it here. And a similar thing we get if we just add two operators s and t. Then the inner product also shows us that we can pull out the addition without any problems. So we just have the adjoint of s plus the adjoint of t. However, now maybe a little bit more complicated, we could also look at the composition of two operators. Then t here might go from x to y and then s from y to z. So here we could have three different Hilbert spaces. And now we know that the adjoint of this composition should go from z to x. Therefore, if we want to distribute this star, the order of the adjoints definitely has to change. This makes sense because s star goes from z to y and then t star goes from y to x. And also this one is really easy to show if you just write down the defining property with the inner product. And I would say if you don't see it immediately, it's not a problem at all, but please use it as an exercise. Okay, and with these properties in mind, you might already see that everything gets much simpler if we only consider one Hilbert space. Because then, if t acts from the Hilbert space x to the same Hilbert space x, then also t star has the same Hilbert spaces left and right. Hence then it's possible to compare the action of t and t star. And in the case that this action is identical, we would speak of a self-adjoint operator. And in fact, these are really important operators, which we will discuss in the next video. Therefore, I really hope that we meet there again, and I wish you a nice day. Bye bye.